Today we're going to be talking about MMF, and what that means is memory mapped files. And we're going to explore a couple of different avenues that we can use those maliciously. Or our presentation is also titled How to Exploit Memory Map Files and Profit.
Yeah, so step one is exploit memory map files, and step two is profit, and thank you, the end. So, my name's Ben Holder. I work for Sirius Security, penetration tester, and web application security guy.
And my name is Parker Crook. I am a solutions engineer at SentinelOne, and apologies for that previous little trope. I threw that out as a random idea. It was late at night. He liked it. He threw it in there, and we kept it.
Yeah.
So moving on, the reason you're here is to listen about...
We're also not developers.
Oh, yeah. One little note is that I meant to bring up is we are not professional developers, so if you see terminology or disagree with a specific thing that I say, please don't take that as a professional discourtesy. We're just, we're hackers, and we like to break things with code. Yeah. So you could call us scripters or script kiddies if you want.
I refuse to accept that.
We want to take just a second to step back and really talk about one of the problems when we're talking about attackers and doing malicious things on your computer. And one of the problems that you have is that behaviors are being, or in some cases have been, categorized by defenders. And what I mean by that is that we're gone away from the day of using signatures to detect something as being bad. And we're getting to the point where certain behaviors are either atomically bad or atomically good. Now, that's a pretty small subset of things that can happen on a system. It's very rare that something, whenever it happens, is always bad. But more in context of other behaviors, you can go ahead and determine that invocation of this API along with another activity on the system, that is bad. That's already been done. There are defenders out there that are able to make those determinations. So what we wanted to do is understand, is there a fileless method out there that doesn't use API calls that have been mapped or modeled to still do malicious activity? That was kind of the genesis of really what we're talking about today.
Right. So we came across this, or looking at memory map files in terms of doing exploit level stuff or trying to hide a payload. Because back in 2016 we were looking at ways that we could pass mofcomp.exe content without it necessarily sitting on disk, so that we could recompile them off and gain persistence on the system. That that particular research didn't prove out anything worthwhile, but it started us looking down the path of what is MMF, what does it do, how does it operate, and how might we be able to leverage putting things directly into heap memory to do stuff.
So hang on just a second.
We'll get there.
So memory map files, if we take a look at the history of memory map files, they really started out on Linux. And the reason being they were created as a way to take files off of disk and put them in memory for high-speed access, so you didn't have latency with disk I/O. So use cases typically were taking database files and being able to access them at high speeds. One of the side benefits was that once you map that in memory, you can share that across multiple processes. So another one of the use cases was being able to load a file into memory and allow multiple processes to access the same piece of data. Yeah. So you only had to load it once. And this was ported over to Windows a long time ago. And the memory map file class in .NET is what we're talking about when we talk about memory map files today.
Yeah. And back when we were doing this research, we found that for the MMF, for the purposes that we were looking at, there wasn't really a lot of solid documentation at that time. But an idea was born out of this, and it was generally the way that the memory map file class is leveraged is for high-speed access. You take an object that's on disk, read the contents into memory, and then that allows the process to go directly to memory instead of having to go to the disk to read the object to go back and process it. It speeds it up. And when you look at the way that the memory map or the MMF is used, is that it either sits in virtual memory or heap memory. And what we wanted to do is to make sure that we dodged the virtual memory portion of it. So we didn't want anything to touch disk, so we started looking at what can we do to use a memory map to get straight to heap. And so most formats of MMF are disk-backed, meaning that they read an object from the disk, take the content, and stick it into memory. If you go and do a count of the methods that are available in that class, there's 11 of them that are disk-backed. There are 4 that can do both. So there are 15 total methods available in that class that specifically operate on accessing and leveraging objects that already exist on the disk. But there are 3 specific methods that allow you to just create a memory map and put content into it without actually having to touch an object on the disk to get that content. So what we looked at is the create new method, and that accepts pretty much any data type that you want to throw at it: a string, a byte, an integer, so on and so forth.
Arbitrary data.
Yeah, pretty much. Sorry, I have little kids and dry weather, so it puts a frog in my throat. All right, so yeah, non-file backed memory map files. So non-persistent files are memory map files that are not associated with a file on disk. And this is the behavior that we wanted to leverage as much as we could. So one of the limitations of this, though, is that when you're done working with that content, when there's no longer a process that's actually accessing that memory map file, the data is lost because it's deallocated and then it's passed to garbage collection. So, they're suitable for creating shared memory or IPCs, for their general operation.
So it's an interesting use case, but it's severely limited. So we just talked about IPC. So in IPC applications, you've got this handle for a memory map file. How do you share the handle between the 2 processes in such a way that you don't cause relinking to occur? Because the goal of using memory map file in memory only from a malicious actor standpoint would be to break that the contextual information between malicious process A and malicious process B and having a shared memory channel. But you would either have to have a static name, and then incident responders or forensic analysts could then understand that those processes were talking because of that static name. Or if you generated dynamic handles for those memory map files, you would have to be able to share that name between the 2 processes somehow, and then that would enable an analyst to relink those together and understand that those processes were interrelated and communicating to each other. The other thing is that once the last process dies that actually had a memory handle, it's collected by garbage collection. So limited use case, definitely not usable for persistence. So
what we wanted to see is what if we could use MMF to actually execute code? Go ahead.
So real quick, a couple of programming fundamentals. You shouldn't be able to readily get addressable memory space without going through memory protection programs like ACCESSOR or DEP. All memory allocation should be going through the kernel. You shouldn't be able to do that from user space. There are a couple of methods that allow you to do this type of memory injection attack. A couple of those are up on the board. Things like reflective DLL injection, process hollowing. A new one that came out last year was process doppelganging, also return-oriented programming. And we can talk about a couple of these just so you understand the difference between existing methods and the method that we're going to be talking about today. So the first one, if we take a look at return-oriented programming, the concept or the core concept is that a return-oriented programmer wants to find what's called gadgets inside a running process. And what those gadgets are chunks of assembly. So chunks of assembly like jump or pop return. In assembly code, basically these gadgets are things that allow you to move execution to a certain space in memory. And basically what an attacker would do is hide something in memory, and they'd need to find a gadget that allows them to get execution over to that space in memory. That's exploiting vulnerable applications in most cases. Another one is invoke shellcode. So what we're doing with invoke shellcode is taking .NET methods that are not native to PowerShell and loading them from kernel32.dll and taking those methods and then making them available in PowerShell, namely allocate memory. So there's unsafe methods that are just not ported into PowerShell. And once you can allocate memory, you can go ahead and create a process, take that memory space, and then create a delicate and point execution there. It's a really roundabout method of doing a shellcode injection or injecting shellcode inside of PowerShell. So the problem is that all of these methods utilize API calls that have been well known as malicious or contextually suspicious. So how do we go back, and can we use MMF?
So, earlier we had said that when we were originally researching and looking into the memory map files, documentation was lackluster. There wasn't a lot for us to read so that we could understand how does this operate, how does it function, and how can we leverage it for our purposes. So we go forward to 2017, Microsoft did a major overhaul of their documentation, and we saw the memory map file class, and that there's a lot of methods underneath that allow us to do some interesting things. So one of the major components is that we found that you could, for when you create your memory map area, or you use a view accessor, which is what has the capability of going back and accessing the content in your memory map. You started to see that you had permissions that you could assign to it. So you had, read, write, execute. And it was the executive function that became really interesting to us, saying, this is a little strange. I'm not used to the concept of being able to throw an execute permission just natively like that to memory. So we formatted a theory, and we looked at, as an attacker, what would you want to do? So you would, generate your malicious content, and you'd use MMF to put that that content into memory, and then what the attacker would look to do is to generate a malicious trigger, something that's going to be able to pass execution back to that position in memory, so when you look directly at PowerShell, the memory map class is directly accessible, and it's a normal use case. So when you go and you load a DLL into memory, you're generally adding it into a memory map so that multiple processes can access it at the same time. So you have one copy in memory that can be utilized by multiple processes. So this is okay normal behavior. So AV doesn't convict it. Whatever the methodology is that we use to redirect execution then points back to MMF, and it runs the code that you put in there. So our original use case was to sit there and figure out how, could we take this concept and could we turn it into something that would actually execute? So we looked at C#.net because we wanted to make sure that all the functionality that we needed was there without having to go and load different assemblies. So looking at the code, the first thing that we do is we declare a variable into a byte array that will hold the shellcode. Whatever it is that we want to use, we just sit there and store it temporarily. We go ahead and we add MMF, or the memory map file, and the memory map view accessor, so we can go ahead and get the methods that are underneath it later. Really what is important to start looking at is underneath the try block. So you see MMF for memory map file, create new, and that's the component that actually creates the memory map for us. You see the component in red where it says, it's __ shellcode, and we were talking about where you have to create a handle or a name for your memory map. That's what this is doing. That's where you would share the shellcode to process A and shellcode to process B, and both of those processes now understand where to go. They know how to access the content of that memory map. We have to declare the length, tell it how long it is, but you look at the memory map file access, you now can actually say, read, write, and execute. So it starts getting us into that position that we're looking at of being able to execute the content.
So that was one of the major points where we moved forward with this proof of concept, was that once we can assign execute permissions to the memory, then we could actually pass a pointer and execute. So as we see here, I'll let Ben take it over again.
So, and like I had mentioned before, the accessor is the component that actually goes back to the memory map and does something with it, accesses the content, reads and writes. So this is where we build the view accessor. You pass it the length again of the shellcode, and then you give the accessor itself the capability to do something. So in this case, we just matched our permissions. So it gets to read, write, and execute the content that's in the memory map. Where you see view accessor.write array, what that is actually taking the content that we had before, the shell code that we generated and stuck into the variable. It now takes that, reads that content out, and then writes it for the first time into the actual memory map. So now it's sitting in the heap. We initialize a variable for the pointer, and what this pointer is it's going to hold the value of where the memory address for the memory map starts. That's what we're trying to pull so that we can pass it to execution. So really the last part that we have to go over in terms of the C# code is we end up having to create a delegate, and we're not really going to go over the the intricacies of what a delegate is and what it does, but it's important to know that this is what we pass, or the delegate is what is given the task to actually go and execute the code for us. So we generate a function that will take the pointer that we referenced before and then passes it and says, go and run this code. So and then late at night, one night I'm sitting there trying to tell you how that doesn't work. But that also does not work, and then I have all of a sudden a calculator. So this is what we were able to do as our very first use case, is just some very simple shell code that popped a calculator. So we used MSFNM just to render command-c calc.exe as opcode so that we could take that and stick that in there. Jammed it into the byte array, and it's really because it's small, it's simple, and it's not its own runtime. It's just making a call via command to the system to do something. So start calc.exe. Really simple, really easy, a very good first use case for us. So remember, the overall concept is that we shouldn't be able to get readily addressable memory to execute code without going through protections like deeper ASLR. You really shouldn't be able to do this from user space in general.
So kind of the next goal that we had once we had this initial proof of concept was, can we make this code portable? So one of the limitations of C# is that you've got to compile it. And once you compile it, it turns into a file. And so now your delivery mechanism is writing to disk. And again, a whole concept was, can we do this from memory? And also when you compile something, excuse me, there are attributes associated with that file. One of those key attributes is going to be the fact that this code was compiled with unsafe methods. So I don't know if you saw the little asterisk in the bottom right-hand corner on one of those slides, but one of those methods is actually an unsafe method. So to compile with it, you actually have to pass a flag that says allow unsafe methods to be utilized.
Because C#.NET is very memory safe. It doesn't, when you start trying to directly interact with memory, that's where you have to create your method and say, this is unsafe. I know I'm not supposed to be doing this, but allow me to do it anyways. Before it'll let you compile, you actually have to pass a switch to your IDE, to your compiler, whatever it is, that allows you to actually compile a program with an unsafe method.
So the idea was made that can we get away from the file and port this code to PowerShell so that you can do just-in-time compilation with the methods in PowerShell. So with that, I want to walk you through our proof of concept code for PowerShell. It turns out getting and creating an MMF in PowerShell is actually pretty easy. It doesn't look like it up there, but basically what we're doing is we're creating a variable called MMFML, and as you can see there, we're creating new, and it's created with a name or a handle of exe. Next parameter we're passing is shellcode length. So before this, in the code stub that I have a shellcode stub, and the shellcode, and then a return, all mapped up into that one variable. And what we need that length for is for how much memory do we need to allocate. If you're dealing with small payloads, it's not necessarily needed. You still need to provide a length, but one of the things to know about memory map files is memory allocations are done in 4K blocks. So in most cases, you're probably not going to need that, but if you're dealing with like a 10K block, you need to know that so that it allocates enough memory for you. Yeah,
the likelihood that your payload exceeds 4K is pretty small.
Yeah, and as you can see, the next option that we're passing is read, write, execute permissions. There are a couple other options that are available to you as overloads that really aren't important for this talk. The next thing we do is we go ahead and create a view accessor, or I'm sorry, a view stream. In PowerShell, there are two methods. There's a view accessor and a view stream. They're different in what they can do. In the case here, what I found that I need to do is create a view stream to actually do the write. It was a bitwise write, and as you can see, we do the write on the next line down there. And then I found out that I needed to do a view accessor to be able to utilize the read to end functionality. So the view accessor allows you to read the entire contents of the stream. And as we can go ahead and see, once I have the view accessor, I can go ahead and utilize a method on that called dangerous get handle. And this is essentially, I like the fact that it's a method on safe memory map view handle. I don't know, safe memory map view handle, dangerous method.
It's very Microsofty.
Yeah. So once you call that, you actually get the memory address of that memory map file. And as you can see, with some manipulation, I can actually return that and print to screen what the location is in memory or in human readable format. So in the bottom here, I've got an example of a memory location of one of my run attempts. And in the bottom right-hand corner, what I've got up on the screen is that I used Process Hacker to show the memory space of the current running process, and I was able to go to that memory location and validate that my code actually existed at that location memory. That was kind of the final checkbox that where we thought it was, based on this mem handle, was actually where it was in memory. And this is where we hit a pretty major roadblock that took me a couple of months to get over, and that's the fact that there is no direct way to do delegates in PowerShell. Now, thankfully, Matt Graber out there has a function called getDelegateType, and it's used in the invoke shellcode that he's got available on the internet. The reason I stumbled with this for a while is that his use of it depends on loading of DLLs to do the allocation of memory and then the accessing of the memory. So it's caused me some stumbling blocks. But we found out is that the stumbling blocks that I was running up against was artifacts of necessary ways of allocating memory through the methodologies they were using. And it turns out that MMF way is much easier because with MMF, we've already allocated the memory. We don't, and we've already found out where the memory address is. So that necessary of loading the DLL to utilize those methods is no longer necessary. So
I just want you to know that he says stumbling blocks, and what he means is like 3-month tirades and Slack of just bad language about trying to figure this out.
Yeah. So it turns out the only thing that we needed to do was create a delegate, since we already had the memory location. So utilizing Matt Graber's getDelegateType function, we had to figure out what we were passing and what we wanted back. Turns out we just needed to create a getDelegateType for int pointer and expect a void function back. Once you did that, you actually do the getDelegate for function pointer call. And I've actually got this broken out on the next slide. So you create the function delegate for the pointer, create the delegate for memhandle, and then you go ahead and pass a memory location to the delegate, and it actually executes your code with that invoke call. So here's a little example. This was my first proof of concept. That's when I took my screenshot, because I was like, oh, it worked. Well, this is the first time I did something other than calc, let me say that. So I used Meterpreter as just a proof of concept. The reason being is our first proof of concept was calc, which was just a simple pass off to an executable
that already exists on
the system or on the disk. Yeah. And here we were actually trying to run interactive shellcode, which is a whole different story.
Right.
So basically taking all the instructions and all the intelligence and putting it completely in shellcode and seeing if that runs. And this was a validation of it.
Yeah, we wanted to be able to prove out that beyond just making calls to things that already exist, that you could load the entire contents of a runtime like a Meterpreter session, so that you could actually run it and get it to function in the way that it's meant to do so. Yeah. So I didn't want to just give you screenshots. I wanted to do a live demo. So what I've got here is I've got a Windows 10 host, and I've put 2 samples up. I've got one out on our GitHub site. This is our code that we've actually published. Proof of concept is actually just launching calc.exe like we originally did for our C# code. So I'm just going and grabbing that code and executing it. There you go. And it's going to launch calc. Now, one of the things that we did with our public code that we published was the PowerShell is going to die in the background, because what's happening when we're passing execution to the heap address is that there's not error handling built in. So once it passes also execution from PowerShell, it's not passing it off as a new thread. So execution actually of PowerShell dies once calc launches. That's okay. It'll probably get fixed here shortly as the community grabs onto this and forks the code and does more things with it. But for now, that actually gives us some artifacts to look for. PowerShell were faulting, and there are specific error codes that I'll publish that you can look for. What does it look like, these API calls and the error logs, when you're invoking MMF and launching directly into the heap. Next code, I'm going to make sure that my Meterpreter session is running, and it is not. So I get to type this live. Windows.
Yeah, no.
Thanks. Yep.
Tab complete takes a while sometimes. Sorry, guys. X64.
Yep.
You know, call me insane because I'm doing a live demo and recording. I haven't learned my lesson. I've done this a few times.
Yeah.
So if I come back over to my host now, then now that my listener is running, I'm going to go ahead and execute this, download the payload, and hit enter twice apparently. So when we pass execution off to shellcode in MMF, our PowerShell process is going to keep running. Now we can fix this a couple of ways. We can run this as a hidden window, but as long as nobody kills this PowerShell process, our shellcode is running. And if I come back over here, I can go ahead and interact with this system. And what's interesting about this is if you're using a sufficiently advanced piece of defense software, at this point, that communication, if you're using something like Metasploit, will be detected unless you encode the payload or use SSL or something like that. This methodology isn't intended to use well-known practices and hide those channels. The MMF invocation is intended as a new way to launch shellcode. So attackers may utilize this methodology, and they may already be using it to launch malicious shellcode that's not known to be bad or unique shellcode in your environment today.
It's really that MSF Venom is just a very convenient way for us to be able to generate payloads, different kinds of payloads, different sizes that that do different things, like calling a command and actually executing the command to bring up calc.exe versus actually creating something that should fully run inside of the heap memory for us.
Yep. So just to recap for everybody, there's a couple of different things that we can do with MMF. So we want to do a little recap for you.
Yeah, go ahead. So it's, one of the points is that, so MMF, or this methodology, allows you to place arbitrary code into memory and makes it, readily addressable. It's something that you can access very easily. As you can see, we were able to gain that actual address back into a variable that we could use to pass execution pretty consistently. And then MMF can be set with the execute permission. It's something that's contrary to what you would expect in terms of direct memory access from user space, and being able to one address to execute and do what it is that you like.
So say for example, one of the methods that we had up on the screen earlier is invoke shellcode. It's very similar in its goals and its path, but one of the differentiations between the two ways that we can inject shellcode into memory is that with invoke shellcode, we're literally loading kernel32.dll from disk. And then we're loading modules or methods that we know are suspicious. Yeah, so defense or security defense products can flag that activity as suspicious, and in context of other activities, say for example, trying to launch directly into that memory address, that's malicious. Yeah. Whereas we're not doing indicators such as loading a DLL. We're just using native API calls in the .NET framework that are natively allowed for PowerShell to utilize, and allocating memory and executing that memory directly.
It's just a kind of a broader example of living off the land. There's nothing else that we have to include. It's already natively available to us. Yep. You don't have to do something. You look at PowerShell Empire, with wonderful, great system. But a lot of the the various modules need to get that extended capability by getting methods and functions from assemblies, so DLLs.
Yep. So some of the other use cases that are potentially available to us with using MMF are things like breaking context for behavioral engines. So going back to those IPC examples, how do I share data as a back channel? How would security products know which memory map files to watch if they're using new handles, things like that. And then another one that we kind of wrote on the whiteboard as an idea is, can we utilize memory map files as a way to bypass like DLP protections to really shuttle sensitive information maybe? We didn't test that. That's something that will be done later, but possible. If so, we definitely need to address it as an industry.
Yeah, so it's wanting to make really the biggest things that we want as takeaways, just for people to understand, is that we're using something that's pretty much allowable. It's given as normal access to people inside of PowerShell and whatnot. So it can be used to do things like maybe hiding data and sharing information between different processes or different memory save spaces. And that's not necessarily something that behavioral engines are looking at right now. So it's a different variation on a theme.
Yep. And so last week as we were finalizing this presentation, I just kind of had an aha moment, and I don't know how feasible this is, and we'll talk about why, but one of the ideas that I thought about was if you're a serious assembler or shell coder, it's possible you could create memory map files as a meta register, so you could take like all the contents of all the registers and shove it into an MMF. So that would be like a snapshot of where I was before and store that data. Or you could create additional registers. So in assembly, you're working with a set amount of registers, and those registers allow you to store locations in memory. And you're working with that finite, so you've got to do things to basically save state or save a register, and you could potentially allocate new memory as a meta register and just store a location of memory there. Again, I said I don't know how feasible that is, because remember, memory map files are 4K blocks, so that's a little insane amount of allocation just to store a little memory address. But it's some ongoing research we'll probably do. But for now, our code is up on GitHub.
Yep, it's available. It's there. If there's anything that you see and you're like, hey, I think that you could do this better, or maybe here's the error handling that you're looking for. Feel free, please, propose it back to us. We'll take a look at it. We're happy to commit other people's changes. It's no big deal to us. On a personal note, for myself and Parker, we'd like, the EFF was actually very helpful as part of this when we decided to pursue this path and make sure that we were not stepping on anybody's toes. So we appreciate their effort on this. Yeah, so just a quick note on that. This is not a vulnerability. We did disclose this to Microsoft, and it works as intended. Yeah. So just a quick note there, but I like that person's face. Yeah. Just like
but we did want to go ahead and thank. There were a couple of sponsors out there for us today that allowed us to do our independent research.
Yeah, so Checkpoint, Cisco, Digital Guardian, Gemalto, and F5 all contributed to us being able to do this independently, so that we could, as individual contributors, come up with something and then propose it back to you guys here at Black Hat. So we really appreciate their support.
Yeah. Great. So, thanks.